Before we discuss this special case of a simply supported beam, let me first set up the context for this discussion. We have discussed that loads are of two types, basically dead and live. Now, dead loads, they do not change their magnitude and they do not change their point of application. So they remain there for this, they almost remain constant for the entire life of the structure. But for live load, it changes uh, with time. Sometimes changes with time means it doesn't mean it's a dynamic load. It means it is sometimes present, sometimes present in small amounts, sometimes present in large amounts, sometimes completely absent. So it depends upon. It's something that varies, changes. Uh, it changes in magnitude and this change is with respect to time. Sometimes it is there, sometimes it is not there. So change with respect to time, and then it also changes its position. Just like consider a truck passing through a bridge. A bridge may be completely unloaded. It may be loaded by a single truck, maybe loaded by a series of cars and other vehicular loading. So live loads are variable. Now this introduces a challenge when we are trying to find the, for example, something. For example, we are trying to find the maximum moment in a beam. Then, since live load may be applied anywhere, so I just to give you an example. For example, if there is a vehicle, and let's say I want to find maximum bending moment in this beam. I need to know where to place this vehicle so that it would produce maximum impact, maximum bending moment. If I'm interested in maximum bending moment, if I'm interested in maximum shear, I need to know where to place this load so that it produces maximum traction at this location. For example, if I'm interested in maximum shear at this location, I need to know where to place this load so that it produces maximum shear at this location, because we are interested in knowing the absolute maximum load effect that can be produced by a loading. So we need to study how, for example, bending moment, how shear forces and how reactions change their changes. How do these load effects changes when live load is applied at different location along the span of the beam, over here, and along different locations. So we need to discuss. Often this is done with the help of considering a unit load. We consider a unit load, for example 1 kilonewton, whatever it is, unit load, and then we for example we are interested in knowing the let's say reaction at A, RA, how RA varies, reaction at A varies when unit load changes its position over the beam. Now if I need to study this, what I can do is I may place unit load first over here, and then I'll calculate this RA. So what I can do is I can make a simple table over here, and maybe the other way I can say that I can define the position of this unit load with the help of some variable, maybe x. I could say when the unit load is at x distance from the left end, what is the reaction at A? So maybe x and then RA. Then I can, let's say this has a span of 10 meters or maybe 10 foot, whatever you like, and then let's say 10 feet, and so this would be, let's say, a 1 kip load. Then I can calculate what would be RA. So you can calculate RA to be equal to, for example, if I calculate RA, this is RB, by taking summation of moment about B, I can calculate this. So if I take this word positive, I can write about B, it would be minus RA times L and plus 1.0 kip times, maybe simply 1.0 times this distance. This is L minus X. Total is L, so this is L minus X equal to 0. So I can see that RA would be equal to L minus X over L. Or I can say it would be equal to 1 minus X over L. So this function will let me know how RA would vary. RA is a function of X in this case. How RA would vary when X changes from 0 to L. So I can plot this and I can see how it varies. Okay? So if this was L was 10 meters, I could say that this would be X minus 10. So this would be 1 minus 1 over 10, 1 minus 0.1 X. I could say it is 0.9 X. Is this right? So when X is 0, this is 1, okay. Okay, let's not take any specific value because otherwise it would be limited to that discussion. So let's do it in a general way. So when X is 0, you put X equal to 0 over here and you see you get the answer equal to 1. So reaction at A would be equal to 1, same as the applied loading. It means you're applying the load directly to the reaction at A and RB would be 0 in that case. Okay, and then when you change X to, for example, something like, maybe you can write it down in a different way to make it a little easier. Or maybe you can say when X is equal to 0.1 L, then you would say it is like this. So 1 minus 0.1 equal to 0.9. So then this would be, so when it is 0.1 L, this becomes 0.9 and so on. You can keep plotting and you will see when X reaches, when you put X equal to L, you get that the answer is 0 for RA. That means you are applying the load directly at B and then all of the load is applied directly, transferred directly to the support at B and no reaction is developed over here. So this, if you plot RA, if you plot RA as a function of X against X, so maybe I can say this is 1 and this is 0, so I could join them by a straight line. This will be a straight line because it's a one linear function. So this line is called influence line or simply influence line. Sometimes we call it influence line diagram, or often we call it influence line, simply influence line. Influence line for RA, reaction at A. This is called influence line. So what does influence line actually tell you? It tells you how a particular load effect, in this case, this reaction at A is our load effect. Okay, so how a particular load effect varies as we place the live load along different positions on the beam. Similarly, you could develop, you could confirm that the RB would be the reaction at B will have a shape like this. I'm sorry. Let me also note this. This is 1 and this is L. In this case, it would be opposite. This would be 1. Then this is for RB, direction at B. This is X. So, and then this is whole length is L. So again, this line is called, this would be called as influence line for RB, direction at B. Now similarly, I could say, if I wanted to know influence line for a shear or moment, I need to specify at which location I'm talking about shear and moment, because these things are variable. I can say construct influence line for, let me show you how. Sorry, need to restart. So if this is the given beam, I may ask you to draw influence line for shear at, let's say, this section. Well, let's call it section 1-1. At section 1-1, and let's say this section 1-1 is at distance x1. Okay. Now, and also for shear, for bending moment at the same section, at section 1-1. So what does it mean? It means, I need your high attention on this point. It means you apply a unit load over here and calculate shear at this location and also bending moment at this location. So what does it mean? X, V, and M. Okay. Now this V is at x1, so I would call it M sub x1, Vx1 and Mx1. This is to tell that I'm finding the influence line for shear at this location 1-1, and so shear at 1-1 and moment at 1-1. So when load is at this location at 0, what is the shear at section 1-1? What is the bending moment at section 1-1? Naturally, this will be equal to 0. All of the load will be directly transferred to the direction over here, and then you will see that the doesn't just simply compresses the beam at this location, doesn't produce any shear, doesn't produce any bending moment. And then when you place the beams slightly on this side, let's say at distance x, then it would be then you can, what you can do is you will have to find again shear at this location and bending moment at this location. It means you will have to cut the beam at this location at section 1-1 and draw the free body diagram. So how would you proceed? You have, this load 1.0 at distance x, and then this is x1. There is a reaction over here, and that reaction, we have seen that reaction would be equal to 1 minus x over L. We have just verified this in our previous discussion. RA. Okay, so what next? You need to know shear at this location and bending moment at this location. You could call it V11 or Vx1, whatever you like. Okay, Vx1 and and similarly Mx1. Okay, and then you need to write the equation for Vx1 and the equation for Mx1. Of course, those are going to be in terms. Let's write down those equations. It would be, you can see, it would be 1 minus 1 plus x over L equal to, x over L. And this would be equal to 1 minus x over L times x1 minus, now this distance would be x1 minus x, so 1.0 times x1 minus x. Okay, so you can simplify this. All right, so you need to write it. The x is something that defines the location of the position load. So we need to write it. So x is the variable in this case. You can simplify it if you like, or you can leave it as it is. Maybe I would at the moment leave it as it is. It is in terms of x. You can understand it. It is in terms of x. Both of them are in terms of x. Now, okay, let's not write in terms of x because it could confuse you with the shear force and bending moment concept. I mean, the previous one. So these are the values for Vx1 and the values for Mx1. Okay, and then you know that the situation will change. So these values are valid. These functions are valid when x is between 0 and x1. So when the load is between 0 and the section 1, you can apply these functions. Maybe you can just remove these. So both of these functions are for this range of x. And then you can move the load onto the other side. I could just copy this. Just copy this. Now load is on maybe on the other side. Over here, and now this is x. Again, you still have to take sections at 1, 1. You still have to take sections at 1, 1. So what does it mean? Now, again, this direction would be 1 minus x over L, and this one would be x over L. So you need to cut the section over here. This is 1 minus x over L. Okay, and I need to know the shear and bending moment at these locations. This time we do not have this load over here. So earlier we were having the load over here, so the free body diagram also included that load. Now the load is on the other side. Okay, so in this case you can again see that Vx1 would be equal to, you can do this in Mx1. So Vx1 would be equal to minus 1 plus x over L, and Mx1 would be equal to 1 minus x over L times, this is x1. So again, it is, you can plug different values of x in these equations and you can plot these functions. Again, you will be able to plot shear and the influence line for bending moment and for the shear force. So you can plot these functions and then you will see that you will be able to draw the ILD for shear and bending moment. So once you have the functions, it should be easy to plot them. We just need to put different values of x. So just need to mention that this is for the case when x is between x1 and L. You have to use this formula, and when x is between 0 and x1, you have to use this set of formula, and then you're just done with it. For shear force, you also need to know, because these functions are discontinuous with respect to shear force, so you will have to be careful when applying these equations. So you can apply these equations. I mean, x can get very close to x1, but on the lower side. For example, if x1 is 2 meter, it can be 1.999 meter. And similarly, on this side, if x1 was 2 meter, then this one could be 2.0001 meter, something like that, just as we did for previously. Now, this is, I mean, called the basic method for drawing ILD. I hope you understand what ILD means and what is the purpose of ILD. There is a quick shortcut method for drawing ILD, which I'll send you in a short recorded video. I'll let you know how to quickly draw in just maybe 5 seconds. You can draw ILD, but I'm already over 11 o'clock, so I would cut this section over here, cut the session over here.